The substitution rule is also one of the methods that are actually used to find or evaluate indefinite integrals. Let's first look at what it says, and then after that I will give you a practical approach to it, and then later I give you examples, maybe one or two examples, and then I will check where are we with the course outlines, and then from there we can start talking about the next topic if possible. Let's first look at the substitution rule. The substitution rule is saying if let's say you have u is equal to g of x is a differentiable function function whose range is an interval I, and our f is continuous. So our f is continuous, is continuous on I. Then the definite integral of this composite function g of x times the derivative of this inside function g prime of x with respect to x must be the same as the as the indefinite integral of f of u du. So what we're basically doing here, we are actually replacing this by u and then replacing this whole thing by du. That is what is happening, because this whole function is not part of the in most cases you'll find out that the multiplication of two functions is not part of the integration table, but when we are changing the variables, this one become part of the integration table. That is actually one of the main rules of the main reasons why we use substitution rule. We are substituting this function by a variable so that the new function we get, it is part of the table. The substitution rule, remember that we did the power rule. The power rule is the reverse of the power rule of derivative, and then when we're talking about basic derivatives of we have a sine function, it is the sine function has a derivative of cosine, and then the antiderivative of cosine is sine, and we had all those basics. Now when it comes to the chain rule, we used it when we had a function that was sitting inside, and we took the derivative of that function that is sitting inside, and then we multiplied. So the substitution rule is actually the reverse of the chain rule of derivative. So it is one of the nice rules that are there. How do we actually do this thing here, or how do we find the indefinite integral using the substitution rule? We only use it if we have a multiplication of two functions. That is the first thing that you must realize. And the second thing, one of these functions is actually the derivative of the inside function. So that is the second rule. You cannot just say I'm just going to use the substitution rule. You can only use if you have a multiplication of two functions, and also one of these functions is actually the derivative of the inside functions, like the way we did when we were dealing with the chain rule. Let's look at the practical approach, or simply let me call it steps of substitution rule. Substitution substitution rule. Step number 1, right, find the function sitting inside another function. The function sitting inside another function, and let it equal u. So we let u to be equal to that function that is sitting another function. The second step is find the derivative. Find the derivative of u with respect to x. When I'm saying with respect to x, I'm not really saying with respect to x, with respect to the independent variable of that function. If that function is the independent variable is t, then we will find the derivative with respect to t. That is, I want us to find du dx. Right. The third step is you want to solve for dx. Right, so that is what we want to find. Once we have this, we have du dx equal to something, then we cross multiply so that we end up solving for dx. And then the fourth step is saying this: replace the inside function. So we replace the inside function by u, and also replace dx by its value. I'm gonna say its value or expression. Let me put a star there. And then the fifth one is saying this: if the variable x is not eliminated, variable x is not eliminated, then we have, okay, is not eliminated, then we have chosen the wrong u. So if it happens that after replacing dx and also u, you end up still having u and x in the same equation, then it actually means that the variable x, the u that we chose is actually wrong. So we have to choose another u. We have to choose another u, or else the substitution rule is not working. Else the substitution rule is not going to work. It's not going to work at all. And then the sixth one, evaluate the indefinite integral. So we want to evaluate the indefinite integral in terms of u. Number 7, replace u with g of x. Remember that we letted our u to be the inside function, so g of x, which is the inside function, which is the inside function. Okay. Let us take some examples here. Let us take some examples. Maybe this is going to make a lot of sense. The first example is saying, of course, use the substitution. Use the substitution rule to evaluate the indefinite integral. The indefinite integral. Use the substitution rule to evaluate that. Given that you have your 2x, and then you have your square root of x squared plus 1, and then this whole thing, I have a dx there. Now, what I want you to realize here, before I can do anything, which is the solution. So I have my solution here, and what I wanted to do, I wanted to find the indefinite integral of 2x times x squared plus 1 dx. Right. Now, and you have this square root, which means we have 1 over a2. What I can tell you here is that if I were to focus only on this function here, which is 2x, I can find the definite integral of this function. But if I were to focus on this part here, focus on this part alone, which is x squared plus 1 raised to 1 over a 2, I can't find its definite integral, because the only thing that I know that revolves around this is when I have x raised to the power n, because its definite integral is x raised to n plus 1 divided by n plus 1. I know how to deal with that. So the problem is, if this function here that is sitting inside here was just an x alone, so that it was that an x alone, I was going to be able to deal with it using that. The same thing, if this was just x, this thing that is sitting inside here, this root, which is, I'm talking about this part here, if that was just an x, I was going to multiply these two and say I have powers of the same base, I add exponents. But now I have a function here that is sitting inside the root. You can see it is sitting inside a root. Now, in the integration table, we don't have a function sitting inside the root. So we let our u to be this function that is sitting in the value of x, because you can see that I can deal with this thing that is sitting inside here. If this was x, I was going to be able to solve this right away. So this is the problem. So this problem here is the one that I let it to be a u. So I will have let u to be x squared plus 1. Then du with respect to x, where is this x coming from? Is because of this dx must be equal to, what is the derivative of that? It's going to be 2x, and the derivative of this is just a 0. And then after that, I can cross multiply and have our du is equal to 2x times dx, which simply means that our du must be equal to dx, and then I divide on both sides by 2x, so I will end up having 2x here is equal to our dx. Now, from this, I can simply say that using the substitution rule that I have my 2x I have my 2x times x squared plus 1 raised to 1 over 2 times dx is the same as I have a 2x. This x squared plus 1, it is the same as u, so I'll have a u there raised to 1 over 2, or simply put, let me do it like this. I have a u raised to 1 over 2 times dx. My dx is going to be a du divided by 2x. This 2x and that 2x, they cancel out, and now I am actually having this thing here, u raised to 1 over 2 du. And now, what is the definite integral of this? Of course, this is a power function, so we'll end up having u raised to 1 over 2 plus 1 divided by 1 over 2 plus 1 plus the constant of integration, because we don't have the lower limit and the upper limit, so we end up having a integration of the constant of integration. And of course, this is going to be u. If you are dealing with 1, you must know that 1 is the same as 2 over 2, and 1 is the same as 2 over 2. 1 plus 2, that is actually going to be a 3, and then the common denominator is a 2 divided by 1 plus 2, that's actually 3 divided by 2 plus the constant of integration. In other words, we'll end up having, I'm going to change this to multiplication, and then this will become in the numerator, this will be in the denominator. We'll have 2 u raised to 3 over 2 all over a 3 plus a c. Of course, if you were given this in a root form, you need to convert it back. So we end up having 2 and then the square root, because we are dividing, so it's the square root of u raised to the power 3 divided by a 3 plus a c, or simply put, you have a 2, the square root, and then inside here, what was our u? Remember that our u was x squared plus a 1. So this is going to be an x squared plus 1 cube all over a 3 plus a c. That is actually going to be the solution of the first example. So I hope you can see how to actually proceed with this example. Let's look at the second example. Let me double check here. I have a 2, so whenever you have this, you divide, you get that. Okay, I think this is 100% sure. Let's look at the second example. We have another example there. The example is simple because this is the second one. Use the substitution rule to evaluate. The substitution rule to evaluate the indefinite integral. Substitution rule to evaluate the indefinite integral. I have this, and then inside I have cot of x dx. So let's look at the solution to that. How do we proceed here? They want us to use the substitution rule. So this is our solution. So take note that our cot of x with respect to x is the same as cot. We know that it is 1 over tan of x. We still have a dx, and of course you can see that this is the same as cosine of x divided by a sine of x dx. Remember that tan of x is equal to sine of x divided by cosine of x. Saying 1 over this is going to switch these two. That is why we are having that. And then if you look carefully into this one here, you will find out that sine is in the denominator. So we are having this function here, and you have sine of x, but it's in the denominator, so we give it an exponent -1 to say it is in the denominator. And then we have a cosine of x dx. Let me use orange then. Now, if you look into the integration table, we don't have the antiderivative of sine of x, and then you have a -1 there. We don't have it at all. But when we are looking for the antiderivative of cosine of x, we do have the antiderivative of that in the integration table. So the problem here is this, because we don't have that. So what we can see is this. Let's leave that for a moment. If I was having x raised to a -1 there, I was going to end up having, this is the same as 1 over x. And in the integration table, I know that the antiderivative of 1 over x is a natural log. But instead of having an x raised to -1 there, I have a function that is sitting in the value of x. Okay, let me repeat, start from the beginning. I have this nice thing here. This one, I know that it is there in the integration table because the antiderivative, of course, is sine. But when we look into this function here, sine of x raised to -1 is not in the integration table. And having an exponent, the only thing that is having something raised to an exponent is actually having an x raised to an exponent n. We know how to deal with that. The second one is having an e raised to some exponent. The third one is having an a raised to an exponent. And this is a constant, this is a constant, this is x. But when you look into this thing that is sitting inside here, it's not that, it's not that, and it's not that, which means that this is actually giving us a problem. So we look for what is inside there, because that thing that is inside is not this x, it's not this e, it's not this constant a. So that is what we let it to be a u. Let u to be equal to sine of x, because it is what is sitting in one of these things that I know that they actually have an antiderivative in the integration table. And then after that I can say then du dx, because we're dealing with dx here. So what is the derivative of sine with respect to x? We know it is cosine of x. And then I cross multiply, because there's a 1 there. I will have du is equal to cosine of x times dx. And then when I'm solving for dx, I will end up having du divided by cosine of x, because I divide on both sides, and then I end up having a dx. And then once I have that, I go back to this thing that I have here or there. It doesn't matter, because this thing and that thing and that thing, they actually mean one and the same thing. So the first thing that I'm going to do, I'm going to replace sine by u. So if you noticed, we were still busy with this is cot of x dx, and I said this is the same as cos of x divided by sine of x dx. Now I said replace sine by u, so this is going to be, I still have a cosine of x divided sine, I said is going to be u. And then what is our dx? Our dx is actually du divided by cosine x. So our x is going to be du divided by cosine of x. And this cosine and that cosine, they cancel out. And now you have the indefinite integral of 1 over u and then du. And now what is actually the antiderivative of 1 over u or 1 over x. We know that is supposed to be the natural log of whatever is the u that is there, and then plus the constant of integration. And what was our u? You go back and look at your u. Our u was sine of x. Therefore, this is going to be just the natural log of sine of x. So we take the absolute value because the ln cannot take negative values there. And also, if you look at our integration table, we know that, let me see if I still have it here. So we had our integration table somewhere there. You can see that whenever you have 1 over x, you must have a natural log of x plus a c. So that is what is important there. I'm not just saying things because I just feel like it. Is what you actually do. So we are having that. Let's look at another example, the third example. Let's look at the third example. Number 3. Use the substitution. Use the substitution rule. Use the substitution rule to evaluate the indefinite integral of, I have an x cube, I have cosine of x to the power 4, I have plus a 2, I have a dx. I wanted to solve this thing here. How do I do it? I need to have a nice solution here. So I'm gonna write my solution somewhere here. I want it to be greenish. Solution. I want to have a solution there. Now, let's start from the beginning. If I were to look at this thing alone here, I have an x cube. I know how to find the antiderivative of that because I just have to add a 1 and divide by the new exponent. If I were to look at cosine of x, I know how to take the antiderivative of that because the antiderivative of cos is sine, because the derivative of sine is cos, so the antiderivative of that is sine. But the problem here, I've just placed a function in the value of x and this function is sitting there. And it is the problem that makes me can't take the antiderivative of cosine of something that is not x. So because of this, so I am going to select my u to be what is sitting in the value of x in this function, which is causing me not to be able to take the antiderivative. So I'm going to say let my u to be equal to x to the power 4 plus a 2, which means now our du dx, the derivative of that is going to be, I bring the 4 down, I will have a 4 times x, and then I subtract a 1, so I'll end up having 4x cubed. The derivative of that is 0. This simply means that, and then I cross multiply, I will end up having a du equal to 4x cubed times dx, and then from there I can just divide by 4x cubed on both sides, and then I'll end up having du divided by 4x cubed is equal to a dx. So that is what we are getting at. Now, what does that supposed to mean to us? It means that I can replace, I had an x cubed, I had an cosine of x to the power 4 and then plus a 2 dx. This must be the same as I will have to keep the x cube. I will have to keep the cos. Inside here, this is what I let to be a u. So this is going to be a u. And then what is my dx? My dx is this, so it's going to be du divided by 4x cube. And then this x cube and that x cube, they cancel out. And now you are left with 1 over 4 times cosine of u du. And then the next thing is 1 over 4 is a constant, so I pull it out of the integration sign, and you are left with cosine of u du. And then the next thing is symbol. What is the general antiderivative of cosine of u? So the antiderivative of cosine of u is going to be, I still have a 1 over 4, so for this one is going to be a sine of u, because if I take the derivative of sine, I get a cos, not negative cos. So the antiderivative of this is sine of u, plus, because we don't have anything here and anything there, a constant of integration. And then this u, I have to replace it back. So I have 1 over 4, and then I have to have a sine, and then this one, we said it was x to the power 4 plus a2, plus the constant of integration. That's how easy this thing is. Some students usually forget this, and of course when you're forgetting this, you're forgetting some of your marks. I hope you can see the difference here, that when we're actually dealing with this substitution, what we're focusing at here is the problem. So here we know how to take the antiderivative of that, but here if we had x, the square root of x, we're going to be able to do that, but we can't now because they have a function inside the root. So because this is a function inside the root, not x, we take that thing that is causing a problem and we say it's our u. In example 2, we did the same thing. When we had a chord, we evaluated and ended up finding out this. I know the antiderivative of that, but the issue is this whole thing. If this was x, I was going to be able to do it. If this was e, I was going to be able to do it. If it was a, I was going to do it. But now it is not. Let me just let it to be equal to a u. The same thing with this one. I know how to take the antiderivative of that. I know how to take the antiderivative, of course, but the problem is in the value of x, I have something sitting there. That is what I'm letting it to be a u. That is what is important here. And then you go all the way until you arrive to some of the interesting things there. Let's take example number 4. Example number 4. Example number 4 is saying use the substitution rule. Substitution. Use the substitution rule to evaluate. The substitution rule to evaluate the indefinite indefinite integral. Hope my spelling is right there. So we have this integral. I have a natural log of x divided by x dx. Ooh, let me see if we can do it or not. So let me place a solution there. So if you look into this solution here, we want to find this antiderivative, or the most general antiderivative of this with respect to x. And of course, you know that this is the same as the natural log of x times 1 over x dx. Hope you can see that. Now, if you look into this, these two functions, in the integration table, you know how to find the antiderivative of 1 over x, and you know that the antiderivative of 1 over x is actually ln of the absolute value of x. Right. Now, what is the antiderivative of this whole thing here? If you look in our integration table, we did not have the antiderivative. We only have the antiderivative, that is that, and also know that the derivative of this is that. That's all we know about ln. So we don't know the antiderivative of this particular function. So this particular function as a whole is actually the problem, because we just don't have the antiderivative of this function as a whole. So we're just gonna let our u to be equal to ln of x, or the natural log of x. And then once we are having that, we just say that I want us to find our du dx. And then du dx, of course, what is the derivative of ln of x? You know that it is 1 over x, as simple as that. And then from there, we can cross multiply, and then we decide to end up having x times du must be equal to dx. So we have dx and we have a u. And then we go back. So when we are taking this ln of x and then divided by x dx, this is going to be the same now as ln of x. We know that ln of x is going to be u, x is just x, and then our dx is going, this is dx. If you look at this, this is dx is equal to that. So this is the same as x times du. The next thing is this x here. Looking at this x and that x, they cancel each other, and then this whole thing now is going to be a u du. And now the next thing is, what is the antiderivative of that? If we know that there is a 1 there, you're just gonna add another 1, and then you divide by the new exponent, and then you add the constant of integration. And then of course you can proceed and say you have a u raised to 2 divided by a 2 plus the constant of integration. Once you leave it here, you can end up losing some marks. Let's end up replacing, but you just need to replace this u by its value. So this u, you know that this u was actually a natural log of x, so it's going to be a natural log of x squared divided by a 2 plus a constant c. That is what we wanted to find out when it comes to this particular definite integral. So at least now you can see some of the nice examples that in this case you know the antiderivative of that, but when it comes to this one we don't know it, so we let it u, because it's not the x that is actually giving a problem here, because this whole thing is just the problem. Unlike when we're dealing with this example here, in this example we know the antiderivative of cosine. The issue was the inside, so we took that inside and we let it to be our u. So I hope you can see those nice differences that are there. Let's look at the last example and see how far have we come. So we have example 5. So let's look at this example 5 here. Example 5 is saying use the substitution rule. Use the substitution rule to evaluate. Use the substitution rule to evaluate the indefinite integral. The indefinite integral. Now I am having this nice integral here, which is x divided by the square root of 1 plus x squared dx. Okay, I want to write the solution, of course. What is going to be the solution to this problem? Let's proceed here. I want to find the indefinite integral of x. I have x times, let me write it like this first. I have 1 plus x squared, I have dx, and also I have x, I have times, this thing is the same as 1 over, I'm gonna have 1 plus x squared, I have 1 over 2, I have a dx there. The next thing that I want us to do here is that I have an x times, and then I'm gonna have 1 plus x squared, and then I have a minus 1 over 2, I have a dx. Now that I have these things here, I want us to realize something. I know how to take the antiderivative of this one here, so I am sorted when it comes to this one. Now, do I know how to take the antiderivative of this? Not a chance. The only thing that I know is that if I was having an x raised to minus 1 over 2, or an e raised to minus 1 over 2, or some constant raised to minus 1 over 2, I was going to be able to take the antiderivative of that, because we do have antiderivative associated with these three things. But instead of having an x or e or a, I have a function that is sitting in the value of these things, and that is the one that is giving me a problem not to be able to take the antiderivative of this whole thing. That is what I'm going to let it to be u. Let u to be equal to 1 plus x squared, so that my du dx is going to be, what is the the derivative of that? The derivative of 1 is 0. The derivative of that is going to be a 2x, and then I'm going to cross multiply, and then I will end up having du is equal to 2x times dx. Of course, if I divide on both sides by 2x, divide on both sides by 2x, I end up having du divided by 2x is equal to a dx. Then I go back to the drawing board, and then I say that, okay, fine, the indefinite integral of x times 1 plus x squared raised to minus 1 over 2 dx is going to be, I'm going to keep the x as it is. This thing here is the one that I let to be u, 1 over 2, and then I have my dx. But my dx is the same as du divided by 2x. What is nice about this whole thing is this x and this x, they cancel out, and now you are left with what I still have that. I have 1 over 2, and then I have u raised to minus 1 over 2, and then I have a du. And then from there, this is a constant, I can always pull it up front, and then I still have this integral here. I have minus 1 over 2, and then I have a du. Once I am having that, I will have 1 over 2, and then this whole thing here, you will find out that you are having a u raised to minus 1 over a 2. I have to add a 1 there. What am I doing? I don't have to have this because I'm not going to evaluate anything. So I have to multiply this by u raised to minus 1 over 2 plus 1 divided by minus 1 over 2 plus 1 plus the constant of integration, because we don't have anything that is there. So this whole thing is just the most general antiderivative. So we will end up having a 1 over 2 times, and then I will have a u, and then 1 is the same as 2 over 2. 1 is the same as 2 over 2, and then 2 minus 1 is going to be a 1, and then I have to keep a 2, Same thing here, we'll have a 1 over a 2 because 2 minus 1 is 1, plus the constant of integration. So I have a 1 over 2. This one, I'm going to change this division sign to multiplication. The numerator becomes a denominator, and the denominator becomes a numerator. And in this whole thing, I'll end up having a 2 over 1 times u raised to 1 over 2 plus a c. Simply put, this 2 and this 2 will cancel out, and now you'll be left with u raised to 1 over 2 plus a c. And this equation we're given in terms of roots, so if possible, let's put it in root form. So we'll have a root u plus a c, and then after that, we did not have a u in the question. I don't remember having a u in the equation. The question was having x and square root of 1 plus x, so we have to replace the u back as 1 plus x squared. So this is just going to be the square root of 1 plus x squared plus the constant of integration. So that is actually going to be the final answer. I hope you can see what we are trying to do here. You look at both these functions being multiplied together, and you look if is this part of the integration table. If not, what is the problem that is making it not part of the integration table? And then that problem is the one that you let it to be a u. And then I am going to end here for now. End here. And then let's look at the course outline and see how far have we covered and what is actually missing so that we can complete our syllabus. We did the review of algebra. One thing for sure, we did it. And then factorization, we did it. Finding roots, we did it. Algebraic equations, okay. And then the number system, we did it. Number system, rational numbers, irrational numbers, we did that. Inequalities, we did them. Interval notation, whereby we're talking about this or that or this set of things, we did that. And also this notation. Vertical line test, we did that. Determining whether a curve is a function or not. Domain, symmetry, we talked about that. And then we also talked about power functions, polynomials, rational functions, algebraic functions, trigonometric functions, exponential functions, logarithmic functions. We did that. We shifted functions, we scaled functions, we reflected functions, we talked about compositions, we talked about power of numbers, we talked about the number e, conversion of bases, and log functions, log, semi-log, and all the laws of logarithms. Inverse functions, general definitions, and then definition of a natural log, range of a function, we talked about that. And then we did limits to infinity, continuity, rules of limits, value of limits, and asymptote. We talked about all of this. And then we went to derivatives, first principle, power and basic rules, derivative of exponential functions, product and quotient rule, derivative of trigonometric function, the chain rule. We did all of that. And then implicit differentiation, we did that. And we did derivative of logarithm, higher order derivatives, applications, we did that. We know local extreme, local maxima, interval, where is it increasing, where is it decreasing, concavity, point of inflation, second derivative test, optimization. We did all those things. I even combined these two into one lesson because when I'm optimizing, this one is also needed, so I just did them both in one lesson. And then we defined what is an integral. When we're doing this, we also included sequence and series, so that we can define this properly. Of course, when it comes to sequence and series, they are not usually set. Some people don't prefer to set them. And also this definition, because it uses much of that, is not usually much set, but the calculations are usually set. And then we talked about definition of definite integral, we talked about that. The fundamental theorem of calculus, we talked about that. And then we started to talk about definition of indefinite integral and properties, we talked about those. And then the method of substitution, which is what we recently talked about. And then that is actually supposed to be the end. Integration by part, integration by parts is not it is not part of your syllabus, so we did not do it. But I believe at this stage that we are almost done, except for one thing that I haven't mentioned, and then we can call it a day. I think it's one or two things. So I want us to talk about symmetry, and then I will leave you alone with your exams. So I want us to talk about asymmetry. This is supposed to be y, and then you have symmetry and integration. It's not a big deal. Integration is just one of those things that we already talked about this, but I want to mention it once more so that at least you understand what is going on. There are two things here. So suppose f is continuous. Because f is continuous on minus a up to a, then we have a. If f is even, so it is an even function, that is f of minus x is equal to f of x, right? You still remember when we're talking about even functions. Then when I'm taking the integral from minus a to a of f of x dx, I should get 2 times the definite integral from 0 up to a of f of x dx. Why is that so? It's because an even function, I'm gonna make a simple example here. This is a bad example. Well, so this is a very bad example. So let's say I am talking about this nice function here, which is f of x is equal to x squared. I'm talking about that nice function. Also this side, this is not gonna be looking good at all. So let me try and make sure that it looks a little bit good. You can see that this is even function, because if I were to place a mirror here, this will become that in the mirror if this is the mirror, and also this in the mirror will become that. So if I wanted to find, suppose this point here is minus a, and this point here and this point here is actually a. So if I wanted to find this area under this curve, I want to find this area. Because I know that this is even, moving from here to there, this area and that area is the same. It is enough for me to just find the area from 0 up to a, because this area here, I know it is equal to that. So finding this area and then multiplying it by 2, I will get this whole area. That is what this thing is saying. This is only true if I know f is an even function. And then the next thing, which is number b, if f is odd, in other words an odd function, simply put, whenever I'm taking minus x and I'm plugging in f, I get minus f of x. Then if let's say I am taking the definite integral from minus a to a of f of x dx, this is what I'm going to get. Before I do that, let me add a page here. New page after. Okay. So I am having a function here. I am having a nice function there. Let me place a Cartesian plane. Place a Cartesian plane. And then remove it. I have a y, I have an x. And then my function is nicely looking something like this. Right. So if let's say at this point, because this is going that way, I have my a here, I mean my negative a, and then somewhere there I'm actually having my a, x is equal to a, and I'm looking for the area. Remember that this is an odd function, because if I were to place, let's say this is going to be f of x is equal to x cubed. If I were to place my first mirror here, this would actually be going like this, and then the second mirror here, it will become this. Or simply put, if I were to rotate this by 180 degrees, this one will actually move here and then it move there. One piece can produce the other piece. So this is an odd function. So this is an odd function. So if I wanted to find the area under this curve, what is important here is this. This area, this piece of area, is going to be the same as that piece of area, because it is to get this portion here, I can get it with that portion. So whatever is produced here will be the same as the area that is produced there, except for the fact that when I'm creating my rectangles in this region, they will have a negative height. So the area here is going to be a negative, but the area here is going to be positive. So because this area and that area are equal, but this one is negative and that is positive, when I'm adding these two areas up, I will end up getting the net area of 0, because I said that this area is a net area. So I will get a 0 there. So for an odd function, the net area is always going to be 0 between negative a to a. But for an even function, it's always going to be 2 times the area of one position. So that is all I wanted you to know. And one thing for sure, I would say all the best with your upcoming exams, because we are done from my side. All the best with your upcoming exams. I think we have touched almost everything. The only thing you might need is to practice as much as you can. Otherwise, if you have this content, you have done all the examples, you followed us in each of these, even those parts that are boring, the theory side of things, you tried and forced yourself to actually do them, then I believe that you are actually good to go. We started little here by antiderivatives. We started here, I think we did this, and then after doing the antiderivatives, we went to sequence and series, I believe. Is this? Went to sequence and series, initial value problems, went to sequence and series and stuff, and all those things. I think you are actually good to go now. I'm going to stop there, like I said.